Okay, so before we get into problems and stuff, I won't be here Monday. I said that. And I'm also canceling my office hour on Tuesday. Yeah, sorry. I won't be here Monday. And yeah, everybody except Naomi is like, you have office hours? No, Tuesday or Monday. On Tuesday, but Wednesday, right? And then the next topic we're getting into is friction. That's the last topic. So we have time to sort of stretch out on stuff a little bit. Let me go through this problem. Kind of tricky. So what number is it? Number 6, I think. Is the set called internal loads and structures? Or just internal loads? Okay. And it looks like this. There's a beam like that, connected to the ground by a pin joint. You have office hours? Wow, that could be really useful. And these angles are 80 degrees. These two are connected by a pin at the center. And there is a pulley over here. And a cable connected to the top of the other one. So the cable goes across to the pulley and then gets pulled back the other way over the pulley. I think that's a given force, 300. Is that right? And then I guess weights have to be neglected because we can't do internal loads with structures if we have distributed loads. And weight is a distributed load when you're doing internal loads. So I think this is all. We just calculate the internal loads in these two beams. So I'll call this member 1, this member 2, and A, B are down on the ground, and then C is where they connect, and then D, E. And we'll just isolate the individual bodies, do Newton's laws. So first, free body diagram for body 1. We have the force from the pin joint. I'll call that RA. At the middle, the only thing contacting body 1, body 1 includes the pin. The only thing contacting it is body 2, so this is the force on 1 by 2. And then I'm going to also lump the pulley in with member 1. And so there are two other forces acting, and it makes sense if this is tricky to figure out at first. Include little bits of the cable as it leaves, little stumps of cable, and then the forces go out of those stumps. This still should all just be an outline. So really what I'm imagining including is the pulley, and then all of the cable that goes around the back of the pulley from the top to the bottom. And so those forces go this way and this way. Do we have any way to know what those values are? Yeah, it's 300, because if it's 300 one place, then as long as that cable's touching nothing but pulleys on its path, the tensions have to be the same everywhere. So 300 there, 300 there. And does it give a like a diameter or radius for that pulley? I have it written here as 0.1 meters. Okay. Actually, I think it's gonna come out in the end. So let's just call this D, or 2R. So rho, force, moment. I'll put the about point down at A. So the rho vector for A is 0. The force is RA X, RA Y. Yes, thank you. You're right. Okay, and the cross product is 0. Oh, and we need lengths for these. The whole thing is 1 meter, I guess. Does it say that? In my solutions, it's 1 meter, I think. I have 1 meter written. What? Oh, okay. Let's do it. So you need both of those bits of information. Let's say that it's 80 degrees in 1 meter. Yeah, that doesn't make it easier, that's for sure. God, I'm glad I didn't try that one. Okay, so then F12, the rho vector is, so it's half a meter from B to C. That angle from the positive x-axis would be 100 degrees. So that's 0.5 times cosine of 100 sine of 100, which is 0.087 negative. Yeah. Well, don't just sit there. And then positive 0.448, something like that, 487. No. Yeah. And then the force vector is F12. And the moment is negative 0.087 F12Y minus 0.492 F12X. And then for the lower 300 Newton force, well, the top of this thing is is at 0.174. And then plus R. So I guess that R is going to matter, isn't it? It is. I'm telling you. So this, let's call that 0.1. That's another thing that you should have known from looking at the problem. Now I've given you everything you need for this problem. All right, well, the top one is at negative 0.174, 0.985. The force is 300 zero. So what's 0.985 times 300? Okay. And so that's for the top one of these 300s. Then for the lower one, it's going to be this, just 0.1 meters lower. So negative 0.174, 0.885. The force is 300 zero. And that is this minus 30, negative 265.5. Okay, so Newton's second law says RBX, RBY plus F12X, F12Y plus 300 zero, 300 zero is equal to zeros. And the moment equation says negative 0.492 F12X minus 0.087 F12Y minus 295.5 minus 265.5 is equal to 0. And so our first three equations are RBX plus F12X is equal to negative 600. RBY plus F12Y is equal to 0. And then 3 is negative 0.492 F12X minus 0.087 F12Y is equal to, I can't do that, 295.5 plus 265.5, well, 561. Okay. And how many variables? We have RB, F12, and that's all. So 4 variables, 3 equations. And then we'll go to the other one. Any questions yet with that? So down at the bottom, we have RA at the pin. What do we have at the middle? Yes, so that's the force on 2 by 1. We already have 1, 2, so that's negative F12. And then up at the top, 300. Put the about point here. So the row vector for RA is 0. Vector is RAX, RAY. Dot product is 0. Then for negative F12, that's positive 0.087, positive 0.492. Force vector is negative F12X, negative F12Y. Cross product is negative 0.087 F12Y plus 0.492 F12X. And then the row vector for the 300 is 0.174, 0.985. The force is negative 300, 0. And so that must be positive 295.5. So Newton's second law says RAX, RAY plus negative F12X, negative F12Y plus negative 300, 0 is equal to zeros. And then the moment equation, 0.492 F12X minus 0.087 F12Y plus 295.5 is equal to 0. So equation 4 says RAX minus F12X is equal to 300. Equation 5 says RAY minus F12Y is equal to 0. And equation 6 says 0.492 F12X minus 0.087 F12Y is equal to negative 295.5. And variables, we had 4 before. The only new one we added, so we had RB, F12, and now we also have RA. So 6 equations, 6 variables. So I'll write out this matrix, and then will a few of you solve this, and as soon as we get a couple people agreeing, we'll say that's the answer. Okay, so equations 1, 2, 3, 4, 5, 6. And I guess I'll go F12X, F12Y, RAX, RAY, RBX, RBY, and then the constants. Can someone read me the coefficients for these variables from each of these equations? So like Equation 1, let's start there. Nobody wrote it down. Nobody. Yeah. I'm going to flip out if no one wrote these equations down. Oh, okay. That makes me feel a little better. You got something written down there on your... Everybody show me some kind of human-made mark on your paper. Okay. 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 Okay, good. All right. All right, I'm back to normal now. Thank you. Yes.
So F12x is 1.
Okay.
RBX is 1.
Okay.
Constant is negative 600.
All right.
Next one is RBY is 1.
Okay.
F12y is 1.
Mm-hmm.
Next one is negative 0.492 F12x.
Negative. Okay.
Negative 0.087 F12y.
Okay. Positive.
Yep.
Okay.
Next one is RAX 1.
Okay.
Negative F12x.
Right.
300.
Okay.
All right, y is 1.
Yep.
Negative F12y.
0. Okay.
Last one is 0.492 F12x.
Negative 0.492?
No. Negative 0.087 F12y. And negative 295.
295. Okay. Anybody already solved it? Let me know when you have it. Yeah. So now let's do this one. Let's do the internal loads for this one. So we know that there's a 300 Newton force there and another 300 Newton force there, and the distance between these is 0.1. And then at the midpoint, there's a force of negative 870.4, negative 1525.9. And then down at the bottom, this is RB, 270.4. And then 1525.9. All right, so that's all the external loads on that member. And that's all given in a coordinate system like this. So we want to switch to, you could do it either one of these two ways. I guess to me, I'm going to do it like this. But you could also, rotate the coordinate system over 90 and get it like that.
You don't have to rotate about point you chose for finding the external load.
No, it doesn't. Excuse me. There's not really any about point. All you're doing is choosing a change in orientation. I see what you mean. Like make that x equals 0 point or something. It doesn't matter at all. Right. It doesn't matter. So you would get different looking functions. So when you did your internal loads, if you rotated it the opposite way I did, we get different looking functions for the internal loads. But then if we use those functions to calculate the internal loads at a single point, our functions would give the same answer. All right, so what rotation do I need for this? Theta equals -80, yep. -80 degrees. And so the rotation matrix is cosine of -80, which is positive 0.174. Sine of -80, which is negative 0.4, no, negative 0.985. And then positive 0.985, and then 0.174. And so now we're just going to go force by force and figure out what these loads are in the new coordinate system. Hey, I have a question. If you had an external couple, like a point couple on this body, and you wanted to change to the new coordinate system, how would you do that? They're kind of two answers, a harder answer and an easier answer, and they're the same. Yes, the couple does the same thing, because remember that couple component, when we're working in the plane, is just a z component. And so, so the z components don't change. That z axis is still the same direction. And so, yeah, the easy answer is any couples, just leave them the same. If you were working in 3D, you'd use, well, a three-dimensional rotation matrix, and you just rotate the couple the same way that you did the forces. Okay, so the 300 Newton force in the old coordinate system is 300, 0. So we're going to go, so for each of the 300s, we're going to go 0.174, negative 0.985, positive 0.985, positive 0.174. So that matrix, oh, I'm going to save this and use it over and over again. Times 300, 0. And can someone multiply that? Okay. 52.1, okay. Point, yeah, it was 5 before. Okay, and there's 2 of those. And then the force F12 at the middle. Oh, that was great. That was a real time saver. Negative 870.4. Negative 1525.9. And what do you get when you multiply those? Okay. Okay, and then the last one is down at the bottom. That was RB. And RB is, so we're multiplying that by 270.4, 1525.9. And what do you get when you multiply those? Negative 1455.8, okay. 531.1. Let's just go with those. Okay, so what that means is Now we have a beam that's long axis is lined up with our coordinate system x-axis. And that means we can just think of it the way that we're used to thinking about it. We have a force at the end of 52.1, 295.5, and then another force 0.1 meters away with the same values. And then in the middle, we have 1351.6, negative 1122.1, and then at the right end, well, when we get into the internal loads, this one isn't even going to come into the calculations because when we do our cuts, we never include the extreme right end, but this is negative 1455.8, 531.3. How many places are there where the subfunctions can change? And another one makes, good, 4, exactly. And so there's 3 cuts.
Oh, that's what I
There's
was, yeah. Those counting cuts.
Okay. Okay, so the first cut is in between those 2 cable forces. So this is for x's between 0 and 0.1. So this is just a little sliver. At the end, we have 52.1, 295.5. And then we have the internal loads. Newton's second law says 52.1, 295.5 plus t negative v is zeros. So t is equal to negative 52.1, v is equal to positive 295.5. So is this stretch of beam in tension or compression? And how do you know? Compression. Tension. So, well, it makes sense if you think of, physically, if you think about this horizontal force pushing and it has to be counteracted by that, then it's in compression. But just looking at the values, negative is always compression, positive is tension. So that negative 52.1 for T means it's in compression. And then the moment equation, this doesn't produce any moment, so plus m minus Vx is equal to 0. So m is equal to 295.5x. And for that little stretch, dm dx is equal to v, so that works. dv dx is 0. Does that make sense? Yeah, there's no distributed loads, so q is equal to 0. And then cut 2 is for x's between 0.1 and 0.2. No, between 0.1 and 0.5. So this time our cut includes both of those two cable forces. 52.1, 295.5 here, and then the other one here. And then the internal loads T, V, M. So Newton's second law says 52.1, 295.5 plus 52.1, 295.5 plus T negative V is zeros. So T is equal to negative 104.2 and V is equal to 591, period. And then the moment equation, there's no moment produced, so our about point is at the left end. There's no moment produced by the force at the left end. There is by the next one. So what's the moment arm for that, the right 52.1, 295.5? What's the moment arm? 0.1, yep. And what's the force? What's the magnitude of the force? If you ever get stuck on this, remember you can always write out rho, force, moment, that'll work fine. But what's the force that, so there's two components. What's the component that matters here that produces a moment? Yeah, y component. So 295.5. And then does that force make it rotate clockwise or counterclockwise? Wrong. Counterclockwise.
I'm not talking anymore.
Yeah. Yeah. And then the only thing we have left is plus m minus vx equals 0. So m is equal to negative 29.55 plus vx, so that's plus 591x. And for that second cut, dm dx is equal to v, so that's good. dv dx is equal to 0, and there's still no distributed load, so that's good. And then the last cut is for x's between 0.5 and 1. So this time we have the force at the end from the cable, 52.1, 295.5, and the other force from the cable, 52.1, 295.5. And then we also have F12. That is 1351.6, 1122.1, 1351.6, 1122.1. And then the internal loads, T, V, M. So Newton's second law says 52.1, 295.5 plus 52.1, 295.5 plus 1351.6, 1122.1, plus t negative v is equal to zeros. So t is equal to, is it? Yep. Pete was going to warn me too, but he was afraid to say anything. So t is equal to negative 1455.8. V, I can't do that one. I can't. It has negatives and positives. I can't do it. What is it? Positive 531.1. Negative. Okay. And then the moment equation. We have a moment arm of 0.1 and a force of 295.5. Clockwise or counterclockwise? Pete.
What?
Clockwise or counterclockwise for that 295.5?
We did last time.
Yes, good job, Pete. It was positive.
That's what I said.
And then the second one, oh, this is negative. Now, what's the moment arm for the 1122.1? 0.5 times 1122.1, and then is that clockwise or counterclockwise? These can be a little confusing. Yeah. So since it's negative, so just think of it as downward, so that'll make it rotate clockwise. So this one's negative. And then plus m minus vx is equal to 0. So m is equal to negative 531.1x, and then what do these two come out to be? Positive. I'll do the sign, you guys give me the number. It's in the 500s. Positive 500 something. $532 point what? Okay, and then it's positive because I moved it over to the other side. So that's the moment. Okay, so those are the internal loads, and then you're supposed to do the internal loads for the other member too. The derivative relationship, dm dx is equal to v, dv dx is equal to 0. There's no distributed load, so those both work. You could do the endpoint checks too. Any questions about that one? So that pulley system looks sort of complicated, but whenever the pulley stuff looks complicated, or whenever any kind of cable thing looks complicated, just include the stumps of the cable that are leaving your isolated body. And I think, I don't know, to me, it makes it easier to think through it. And then the other tricky thing about that problem is that, you know, there was all that information you needed that I didn't give you. Yes. Yes. dm dx has to, at every point, be equal to v, and negative dv dx has to be equal to q, where q is the value of the distributed load, the total distributed load at that point. So in all these where we're rotating the coordinate system, since we didn't even talk about how to do that with distributed loads, we can't have any q. Q is always 0, so that says that v always has to be a constant. Any other questions?
Which way is clockwise again?
It's like, think of how a clock goes. That's a nice way to think about it. You should make like a little clock, and then you can be like, because the hands always go towards higher numbers. That's sort of the way to think about it. Just make a little clock, and I'll put it on the back with the solutions next time, with the equations. Yeah.
In like 5 years, you're gonna have students that have no idea.
That's true. That's a good point.
They're like, what?
Yeah, that's true. That's funny. Yeah, that's true. At the Science Museum, I took my kids to the Science Museum, and there was a thing that like told you information about forests or something, and it was like you picked up the phone and like listened to it, and they're just like, they had no, like, what is that thing? Like, what is that? You know, they've never seen a telephone. Right. Any other questions about that problem? All right, let's go on to the new topic, friction. Yes. So we are going to talk about friction and statics in 3 sort of different areas. The first one is square-threaded screws. I have a 3D printed example of this. I got to find it. Maybe I'd lend it to Sue. You have her cell phone number? Can you take Sue and ask her, like, did I tell you that? So I needed to get a hold of Sue because I didn't know where this meeting was, and I ran into Naomi, and she had Sue's number so I could call her. I was like, where's the meeting? And she wrote back, who is this? Kasahara, the physics, everybody's favorite physics teacher. Yeah, right. Susan Kasahara, Dr. Susan Kasahara. Just some. The second topic is belt friction. And the third topic is broken up into 2 parts. This is bearings. We're going to do 2 types of bearings. Journal bearings and thrust bearings. And so I'll just go through these one by one. Square threaded screws is first. And square threaded screws are like this. Yeah, I'm going to try to, but it was nice when I had that 3D printed thing that before I met Sue. Yeah, exactly. Okay, so if you think of, so think of this as like the the nut or whatever is interacting with this screw. I'm drawing a cross section here. Okay, so we're taking a slice through a square threaded screw and the nut that it rotates inside. The screw looks like this. There's the threads of the screw. You might think, like, why don't they make those parallel? That would work better, but that's just my drawing. Yeah. Should have drawn you know what I should have done is draw the threads, and then I'm going to fix it actually, because somebody's going to be looking at this like at midnight the night before the test and get like caught up on that. Like, why does the third one have to be so out of whack? I don't get it. Okay, so the red is the screw. And it's every point on the thread of the screw. You know, if you have a little hammer or whatever, a little checkpoint at one point on the thread of the nut, every point on the thread of the screw at some point passes that. So the thread on the screw is little by little just snaking its way up that whole path. So this is square threaded because of the shape of the threads. So as opposed to this. Good job.
Being an artist.
Yes.
Yeah, he's working on getting us a fine arts. Oh yeah.
So this is not a square threaded screw because the cross section of those threads is not square. So what's the benefit of square threaded screws, and what's the benefit of this? Well, this one is cheap and easy to make. So that it has a lot going for it. That's why, you know, if you go through the fasteners section at the hardware store, you know, almost everything or everything everything in this cheap section is like this. But square threaded screws have the advantages, two advantages, I guess they're sort of related. That first, because there's no, so this is pointed here, if you apply a big force to it, there's no part here that trails off to zero thickness. And so these are a lot stronger. And so if you have to have a screw supporting really big loads, this is a better way to do it. It won't break. Another reason that it's stronger, besides just the thickness, is that if you think of, so there are two types of forces that the nut is applying to these threads. One is a normal force, and then the other one's a friction force. And if you think about the direction of the normal force, that nut is applying a normal force that's at an angle, you know? And that means that the screw is applying a normal force to the nut that's on an angle like this. And so as that force gets bigger, that screw is trying to like explode that nut, you know? It's applying a force pushing the threads apart. There's nothing like that happening here. And so, the square threaded screw doesn't apply an outward force to the nut. And so square threaded screws are what they use on car jacks. Because you're relying on those threads to support a lot of weight. Now, how are we going to treat this mathematically? Well, it's sort of a cool idea. The idea is that so how we treat this depends on an odd fact about drive friction. And actually, that brings up something too. Keep mentioning this, but all of the types of friction that we're going into are dry friction. If you're talking about like well lubricated areas, you know, saturated with some kind of lubricant, you have to deal with fluid dynamics to talk about the friction effects, and we're not doing that. So all of these things are relevant only for dry contact. It can use like dry lubricants. You know, this is relevant for like graphite things that are filled with, you know, graphite lube or whatever. But if you're talking about two things moving through a significant amount of oil, these calculations won't work.
What quantifies as significant?
If the fluid effects of the oil are bigger than the dry effects of the two surfaces against each other. But I don't know. Practically speaking, I don't have like a rule of thumb for that. Yeah. That's a good question. I don't know. I would guess that you could use this pretty well in that case, but you wouldn't want to do it in a case where, like, I guess the question you have to ask yourself is, like, what a fluid does is the velocity of like a moving surface or plane of fluid is proportional to the force you're applying to it. And so if you're talking about like I don't know. Yeah. I don't know the answer to that. Yes. So how we treat this depends on an odd fact about dry friction. So you remember this formula that says force of friction is equal to, well, there's static friction and kinetic friction, but both of them relate in some way to this formula, right? What's missing from that formula that you would, like before you saw this, maybe even now if you haven't thought about it this way, you'd bet your life that the friction force depended on the surface area. You know what I mean? Like what this formula says is, if you look up the coefficient of friction between this rubber and this cable, and you apply a normal force of 100 newtons to it, the friction force is going to be the same whether that rubber surface covers this entire table or whether it's, smaller than this. It's supposed to be totally independent of the surface area. It only depends on the coefficient of friction and the normal. That's an approximation. Apparently it's not a super great approximation, but if you're trying to, get just an estimate, it works okay. So this friction force doesn't depend on the surface area of contact. That's weird. That doesn't feel right. So just be in that feeling for a second. That doesn't feel right to any of us, but that's how it is. And so what we're going to do is we're going to imagine that the thread of the screw is all concentrated into a single rectangular solid. So if this is the thread that it's interacting with, and this is the screw, instead of the screw having threads that go all the way around, we're going to imagine that this is what the screw's thread looks like. So that little protrusion right there is the entire thread. Okay. Can you picture what I'm talking about? No, okay. Well, so what the screw would normally have is, so the thread wraps all the way around, right? And all of that thread on the screw slides around this path as it goes up the nut. Since the friction force, the total friction force, doesn't depend on how long that thread is, how much surface area of thread there is in contact with this, we'll just assume that that entire thread that's really very long is just concentrated at a single location, and that single location is just little by little working its way up the nut. And if we do that, then we can think about a friction problem as being an inclined you know, like a box sliding on an inclined plane, like the physics problems that you did when you first saw friction. So, to somebody looking at it from this side, or actually, I suppose the other side makes more sense. So, to this guy, yeah, teeth. Yeah. What he sees is a ramp with a box sliding up it. This thing is the thread of the screw. This is the thread of the nut. There's a downward force that's the weight it's supporting.
Is that supposed to be completely vertical or perpendicular to the surface?
What?
The weight.
Yeah, that's a good question. That's supposed to be totally vertical. So that's being applied parallel to the screw. And then there also has to be a horizontal force that's moving this screw around. So this is the force that you have to apply to turn the screw. And so this problem is always going to come down to this. An incline with an angle of theta. And a box with a downward force W and a force, an applied force Q. It can go one way or the other depending on whether you want this to go, whether you want to bring this screw down or bring it up. So notice this setup is to move the screw against the applied load, the weight. If instead you wanted to move the screw with the applied load, the Q force would go this way. Okay, any questions about that setup? All right, well, I just give you some more like review homework to work on. We're not ready to work on friction problems yet, but on Tuesday, we'll get back into this. We'll get to some example problems and stuff and see how it works. Okay.